So we've learned how to conserve energy in closed systems. Then we learned how to account for mass as it's moving through open systems. But the reason that we did that was because we want to eventually understand how we conserve energy in open systems. So the topic for the lecture of today is how do we use the first law of thermodynamics for open systems when mass is moving through the system. So we know that we can have systems where mass moves in and out. For example, we can have something like this car engine, which has an air intake and an exhaust. There's also fuel coming in, and then the products from combustion also go out the exhaust. So here we have a system where we can look at all the air that's coming in, we can look at all the air that's going out, and we can look at how that energy change happens and how we're harnessing that energy change in order to create mechanical work. But in order to do that, we're going to have to understand something about the first law for open systems. So we've kind of had this framework for how we approach open system problems. I'm going to tell you that there are basically three big questions that you want to be able to answer when you do these open problems. The first is you have to know where your system is. So you have to figure out how are you going to draw your control system? Where does your control system go? You need to figure out what happens to the mass, and that's why we've been learning about continuity or conservation of mass. And then finally, what we're going to talk about today is how do we account for the energy? Now, some of this we've already seen in closed systems, but in open systems, we have this added complication because every bit of mass that's coming into the system and every bit of mass that's going out of the system carry energy with them. So we need to be able to understand how we account for the energy that's moving in and out of our system because the mass is moving in and out of our system. And that's going to be the topic for today. How do we use the first law for open systems? So this is the wording, right? And again, I'm not a huge fan necessarily of writing out the first law in words, but what this says is the change in the amount of energy stored within a system during some time interval is equal to the net amount of energy transferred into the system by heat transfer from the surroundings during the time interval minus the net amount of energy transferred out of the system on its surroundings during the time interval. One thing you might notice about this wording of the equation, some of this maybe is not unexpected from our work in closed systems, right? Because we talk about heat transfer, right? And heat in being positive, but there's no wording here for work. And we're going to see why that is as we move forward, because it turns out that the work term is kind of going to get wrapped up into this net energy transferred out of the system. Remember, work out was positive, so the work is going to be wrapped up in this net amount of energy transferred out of the system. So remember when we were talking about closed systems, we had the change of energy in the system is equal to the heat transfer in minus the work that goes out. Right? Now, we could take a rate form of this equation. Basically, we divide all the terms by delta t and take the limit as delta t goes to 0. And now this starts to look a little bit like our conservation of mass equation. So here we have this dE by dt term. This is telling us how much energy is either stored or depleted in our system. Now, these terms, where we have dots on top of them, Q dot and W dot, these are rate terms. Just like we have the mass flow rate, how much mass is either coming into or out of our system. Q dot is the heat transfer rate. That's the rate at which heat is entering the system. And the W dot, that's the rate of work coming out of our system. Now, we can talk about that as rate of work, but remember, work is in terms of energy, something like joules, and you might remember that joules per second is watts, right? So this W dot term is the rate of energy leaving the system, but that's the same as the power. So W dot can be thought of as the power that's leaving the system. So can we still transfer heat in an open system, right? So again, so let's say that this is a duct, right? We've got some air running in here and it splits off in two different ways. Well, sure, I can still add heat. So I could wrap this in something that looks like maybe a thermal blanket or something. You plug it in, and now it's generating heat, and some of that heat is going to go into this duct. So sure, I can transfer heat. And can I still get work out? Right? So for open systems, when we talk about work, the answer here is yes, we can get work out, right? So what if we have air that's running into this system, right? And it branches off. But what if in the middle of our system or inside of our system, we put something that looks like a fan blade, right? This is kind of what happens inside of a turbine, right? Where we have these blades that are inside our turbine. We let some high pressure, high temperature steam run through our system, and it expands across these blades and causes that shaft to spin, right? So here, usually, if we're thinking about work in an open system, I'm looking for fan blades. So fan blades either that are harnessing work like in a turbine, or maybe it's something like a pump or a compressor where I'm driving those fan blades to increase the pressure of my working fluid. So this looks kind of like a closed system, except we have mass that's running through it. But ultimately, we can still transfer heat in and we can still get work out. So energy comes and goes with the mass. And that's sort of the big difference here between open systems and closed systems. In closed systems, maybe the amount of energy stored inside our mass was changing over time. But here with open systems, remember now we're looking at positions. So my energy that's coming in with this mass flow rate in might be different than the energy that's going out with this mass flow rate out. So I need to be able to track or account for the energy that's entering and leaving my system with the mass. So how do I do that? Right? So here I'm going to keep my equation. It looks like this is kind of like the closed version, the rate version of the closed system equation. But now I got to add some more terms. So this is going to be the energy that comes in with the mass, or the rate of energy that enters as the mass comes into my system, and the rate of energy leaving with the mass going out. So I have these two other terms, right? So here I can think about this equation as, my dE by dt term, right? This is the time rate of change of energy contained within the system. So am I storing up energy in my control system, or am I depleting energy in my control system, right? So here, now we have the net rate at which energy is being transferred in by heat transfer. This is Q dot. The net rate at which energy is being transferred out by work at some particular time, right? Because this is a rate equation. So all of these are instantaneous rates. And then we have the net rate of energy transfer into the system accompanied by the mass flow. So how much is we take the energy coming in with the mass minus the energy going out with the mass, right? So here now we have this W dot term. So how is it that we figure out how much work is either performed by the system on the surroundings or performed by the surroundings on the system? So here we can think about a pipe. Now, it's kind of interesting, right? Because we know from conservation of mass that if we're running some mass flow through this pipe, it can't slow down, right? Because we have conservation of mass. So if the cross-sectional area stays the same, and I have some mass flow coming in here, and the density of my fluid stays the same, and the cross-sectional area of my fluid stays the same, then the velocity has to be the same everywhere in the pipe, right? And maybe that makes sense to you, right? But maybe you're thinking about, well, if I take a ball and I roll it down a hallway, eventually it slows down, right? There's this dissipation of energy from things like friction, right? So does that mean that flow through a pipe is frictionless because the flow is not slowing down? The answer is no, right? But we still do have to lose energy. So we don't lose energy in terms of kinetic energy because conservation of mass requires, in this case, that the velocity stays the same. But we lose some potential energy in the flow. So what happens is as we move along this pipe, the pressure drops. So we have a pressure drop in the pipe, right? So we pay for the motion in the fluid by this potential energy. So we have less potential energy stored in the fluid because the pressure is dropping, right? So here, if we look at this total work, this or the rate of work or the power, so this is going to be the power from whatever fan blades we have in the system, plus this sort of pressure work or the rate of pressure work across our control system, right? So this W dot term is the total rate of work. W dot from the pressure is the rate of work due to pressure, because there's this pressure difference on opposite sides of our control volume. And then the rate of other work not due to pressure, right? So basically, if we have fan blades inside of our system, then what's going on from that W dot term? So how do we figure out the work from pressure, right? Or the power from pressure here? So what we do is we take the sum of the pressure times the area times the velocity of the fluid that's moving at that control surface, right? So here we would do this. We'd add this here at the inlet and here at the outlet, right? So again, we might be skeptical of this, but we can check the units, right? So we have a pressure, which is newtons per meter squared, times an area, that's meters squared. So that's going to cancel out. So I have newtons times velocity, which is meters per second, right? So Newton meters per second, that's joules per second, and joules per second is watts. Watts is in power, right? So this is a rate of energy over time. So that's good, right? So here, what we can do, we can rewrite this equation as the mass flow rate at the inlet or the outlet times the pressure times the specific volume of the fluid at the inlet and outlet. And this is nice because now this is a function of the mass flow rate in two independent intensive properties, right? Again, we want to be a little bit skeptical here so we can check the units, right? Kilograms per second, that's mass flow rate. Newtons per meter squared, that's pressure. Meters cubed per kilogram, that's specific volume. So the kilograms are going to cancel out. Meters cubed divided by meters squared gives me meters. So I'm going to get newtons times meters over second, which is again joules per second, right? So maybe you believe me, maybe you don't, right? This equation's in the textbook, so it's, it's valid, right? So the units work out here, right? So this is always a trick that we can do, whether we're on a test, whether we're just trying to think something through. If you're not sure about an equation, check the units, right? So now we're going to add this in, right? So we're going to break this total work term down into the work from the control volume. So this is the power that's either generated or applied by whatever fan blades we have in the system. And then we have these pressure work, which turns into sort of a rate of pressure work or pressure power terms that are in here too, right? So we add up all of these pressure terms at the inlet and we subtract all the pressure terms at the different outlets. Okay, and then we have plus all the energy that comes in with the mass minus all the energy that goes out with the mass, right? Although these are rates, so it's power coming in with the mass and power going out. So how do we define this E dot term, right? So what's the energy that's coming in with the mass? So we know that energy, total energy, is a sum of all the different kinds of energies that we can add, right? So in this class, the kinds of energy terms we're going to put in here, right, are going to be the specific internal energy, the velocity squared divided by 2, that's a kinetic energy term, and the gravitational acceleration multiplied by a height, that's a potential energy term. We're going to multiply all of these energies by a mass flow rate, and that's going to give us a power or a rate of energy that's coming into the system, either at the inlet, right, or leaving the system at the outlet, right? So the blue term here, U, is internal energy. The orange term is kinetic energy, and the green term is gravitational potential. So if we knew all of these terms at the inlets and the outlets, then we could put them into our equation and we'd be able to figure out all of the energy that comes in and all of the energy that goes out because there's mass coming in and out of our system. So again, let's check this out, right? So we have a mass flow rate times a specific internal energy. So that's kilograms per second multiplied by kilojoules per kilogram. So if you look up specific internal energy in the textbook, typically you'll get kilojoules per kilogram. And this is going to be kilojoules per second. And that's kilowatts, right? Because remember, a joule per second is a watt. So this is a rate of energy. Let's move on to the kinetic energy term. So now we have the mass flow rate times the velocity squared divided by 2. So this one gets to be a little bit tricky, right? So now we have kilograms per second. That's our mass flow rate. Velocity squared, right, is going to be meters squared divided by seconds squared. Or divided by 2 doesn't have any units associated with it, right? So now I'm going to do a little bit of sleight of hand here. So I'm going to change this to 1 over seconds, right? And I'm going to multiply the kilograms in here and get kilogram meters per second squared. But now I have 1 meter left over. I'm going to put that over here, right? Now, a kilogram meter per second squared, right? This is mass times acceleration. Mass times acceleration is force, right? Newton told us that. So now we have 1 over seconds times Newton meters. So this is joules per second. So this is watts, right? And that's good because we're trying to get something in watts or in joules per second, right? It's a rate of energy entering our system in this case, right? But if we remember when we did U, that was kilojoules per kilogram, and this is only, or kilojoules per second, and this is only joules per second. So this is not going to work out exactly the same every time, but if the kinetic energy term survives, right, if we're interested in kinetic energy, we have to be worried about the units. So if we want to turn this into kilojoules per second so that so I can add apples to apples when I'm going inside my bracket here, now I would multiply by 1 kilojoule divided by 1,000 joules because I want to get rid of the joules on top, and there's 1,000 joules in a kilojoule. So if I'm going to leave this as v squared divided by 2, but if I was doing this problem, I'd have to look and see, okay, what is my velocity measured in? And if it's in meters per second, and this is a metric problem, then eventually I'm going to divide by 2,000 here. But it's going to be different if it's kilometers per hour. So I don't want to put the unit conversion in here automatically. I want to leave it like this and then think about it when I'm actually doing the equation. The gravitational potential energy term is somewhat similar. So again, we have kilograms per second multiplied by an acceleration, meters per second squared, multiplied by a distance, meters, right? So kilogram meters per second squared, again, is going to be newtons. So this is going to be Newton meters per second or joules per second. So again, if this potential energy term survives, then I'm going to have to add in this extra unit conversion factor, right? And again, it might not always be dividing by 1,000 because maybe I'm talking about a height in kilometers or something, right? So here, I have to remember basically that if my velocity term and my potential energy term survive, I really have, my spidey sense should start tingling. I really have to worry about the units there because naturally I will get different units than if I get specific internal energy from my textbook. So I can do this at the inlet and at the outlet, right? And now I have an equation for open systems if I'm trying to conserve energy, right? But this is a little bit messy, right? And I can simplify it a little bit because you'll notice I have a term here that's the sum of m dot in times p and v in, right, at these inlet ports, right? And then this term is also multiplied by the sum of all the mass flow rates in, right? And this term here is multiplied by the sum of all the mass flow rates out, just like this term here is multiplied by all the sum of the mass flow rates out. So I can collect like terms here, right? So the terms here circled in red go together, and the terms circled in green also go together, right? And if I do that, my equation gets a little bit simpler, right? So now this is looking nicer, right? So I've got that, the rate at which energy is being stored in my system is equal to the rate at which heat is being entered minus the work that's produced or added to the system from fan blades that are inside my control volume. And then I've got a bunch of energy terms that I evaluate at all the inlet ports minus a bunch of energy terms that I evaluate at all the exit ports. But you got to remember, as engineers, we try to be efficient, right? So here I've got this specific energy plus pressure plus specific volume term. Now, anytime I fix a state, I know all of these terms, right? Because once you've fixed the state, once you have two independent intensive properties, you know all the intensive properties in the system, right? So I can make my life a little bit easier if I define a new variable here, right? So we're going to take the specific internal energy plus the pressure times the specific volume, and we're going to define a new term. And that term is going to be the specific enthalpy. So it's symbolized by little h. So we had seen this a couple of times, maybe in tables when we were looking up, maybe in some of the problems where we had to fix states. They told us find the specific enthalpy, right? And it's just, the process is just like finding the specific internal energy, but we're using different columns in the tables, right? Or if we have an ideal gas, instead of having CV times delta T, we have CP times delta T, because enthalpy has a P in it, so we use CV times delta T, right? But enthalpy, the definition of enthalpy is the specific internal energy plus the pressure times the specific volume. And the reason that we do that is so that I don't have to look up the specific internal energy and the specific volume in tables. Because once I fix the state, all this stuff is dependent on each other. So I might as well just find H. So once I find H, then I can put this in. And now my first law equation gets easier, right? Or at least more simplified. Now, there's going to be a temptation as we move through for you to say, oh, this is this kind of a component, and the first law answer is this. I am going to tell you to resist that temptation. Why? Because I think that every problem we're going to do with open systems, you're going to get the right answer if you start off with the full version of the first law, right? So all of this stuff, I know it can be a pain to write down, but it doesn't take all that long, right? Plus, when you write down the whole version of the first law, then you're forced to show me that you understand which terms are important for which kinds of components. So what we're going to find is that we're going to make a bunch of assumptions depending on what the component is, and that's going to cause a bunch of these terms to drop out, and we'll get simplified versions of these equations. But if you always start with the first law, you will get the answer right. And if you trust the first law, you will get the sign of the answer right. Now, it's a little bit weird in the textbook because sort of for the first half of the textbook, it talks about this hip to win convention. And then somewhere in about the middle of the textbook, it says, well, let's just treat all these terms as if they're absolute values. I am going to encourage you not to do that. And I'm going to encourage you to always use the first law, because then you don't have to worry about which values are supposed to be positive and which values are supposed to be negative. You just put the information you have into the first law, and you trust this sort of bedrock equation for thermodynamics that helps us understand the universe. So please trust the first law, right? So we've talked about steady state systems, right? And steady state systems are really important because a lot of things like a nuclear power plant, it takes a little while to warm up, but then we run it for a long, long time and things don't change, right? And if things don't change with time, then that means that anything that measures the change of something with time must be zero. So if we're at steady state, nothing's changing with time, which means that the amount of energy stored in our system is not changing with time. So if we're at steady state, which we basically are for every problem or virtually every problem we're going to do in this class, then the derivative term here goes to zero because we're at steady state. So if you write down this equation and you draw a line through it in a zero, just like I've done here, then you're demonstrating to me that you understand that the system is at steady state. Now, this is a great equation. There comes a problem when we're dealing with imperial units. Right? Now, as I've said throughout the class, like me, probably by the end of this class, you're going to come to really dislike these imperial units, because it's always a bit more difficult when we are tracking units in imperial units, right? So if we're using things like feet and inches. So we know that these two terms, this velocity term, the kinetic energy term, and the potential energy term, they're tough even in metric, right? I got to watch the unit conversions. I'm probably going to end up dividing both of these terms by 1,000 if we're dealing with metric units, right? So they're tough even in metric, but it's even worse in imperial units, right? So we got to remember these two terms where we would worry about the units, right? We have to divide by GC. Remember we talked about GC, and it's this kind of sleight of hand that they added to the imperial system so that 1 pound of mass weighed 1 pound on Earth if you're at sea level, right? So that same kind of trickery comes in these terms, right? So we got to add this divided by GC term to these. And then we got to worry about the units, right? So if you have a problem that's in imperial and the kinetic energy and potential energy terms are going to survive, then you have to worry about this GC thing, right? So we got to, these two terms, we got to divide by GC, right? So now I'm going to take you through the units to make sure that we're adding apples to apples, right? So we got a mass flow rate times enthalpy, right? So this is going to be pounds mass per second multiplied by H, when you look it up in the textbook, is in BTU per pounds mass. So that's going to be BTU per second. Okay, so now let's say we have mass flow rate multiplied by this kinetic energy term, right? So mass flow rate, pounds mass per second. The velocity squared, let's say the velocity is in feet per second. So this is now feet squared per second squared. And now GC kind of has this weird looking units, right? So GC, because it's an acceleration, has this feet per second term, right? Remember, it's on the denominator, so I flipped all this up. But then we use it to get rid of the pounds mass and put the pounds force in, right? So it's kind of got this weird looking unit, right? So now if I multiply all this stuff together, right, my pounds mass are going to cancel. My seconds squared are going to cancel. I'm going to cancel out one of these feet, so I'll get foot pounds, right? That's pretty good. Foot pounds is energy per second, right? So that's good because this is supposed to be a rate of energy that's entering the system, right? So it makes sense to have foot pounds per second. Unfortunately, though, when I looked up H, I got an answer in BTU per second, right? When in here for H, I had BTU per second, right? So now I want to change, I want to get rid of foot pounds. Foot pounds and BTU are both units of energy, right? And naturally, it's a nice round number like 778, right? I don't know if you can, maybe you can't tell the sarcasm there, but right, this is why we love imperial units, because the conversion factors don't make any sense. So here we're going to cancel out these foot pounds, right? We're going to divide by 778 so we can get BTU on the top. So this velocity term, if it survives and you're doing a problem that's in imperial units, first you have to remember to divide by GC. Then you got to remember the funny units of GC. Then you got to remember to change probably from foot pounds per second to BTU per second. So you got to remember that conversion factor. We get the same thing when we deal with potential energy from gravitational, right? So here, again, we got a mass flow rate. We get feet per second squared. That's G, right? GC still got this funny unit. It's in the denominator, so I flip them over. And then I multiply by feet. And again, we're going to get foot pounds per second, so we got to convert that from BTU, right? So remember, the gravitational potential and the kinetic energy terms are always going to be a problem. Doesn't matter if it's metric or if it's imperial. But it's a bigger problem if you're dealing with imperial units, because first you have to divide by GC, and then you have to deal with this conversion factor, BTU BTU to foot pounds force. So the take-home message is, if kinetic and potential energy terms survive, it's always going to be a pain. It's less of a pain in the metric system, where you're probably going to have to divide by 1,000. It's more of a pain in imperial units, because first you're going to have to divide by GC, and then you're probably going to have to divide by 778. But those are only what you're probably going to have to convert by if you're dealing with things like meters per second or feet per second. So it's better to just leave the equations like they are, but then think about what the conversion has to be. Okay, so now here's where we start to get interesting, right? Because the really cool thing I think about thermodynamics is this is one of the first classes as an engineer where I think we get to start to understand this idea of system integration, right? So the way that we approach thermodynamic problems, so this is kind of a very simple version of a coal-fired power plant or maybe a nuclear power plant, right? Where what we do is we have some water, we pump it up to a high pressure, then we boil it, right? So maybe we're burning coal to make heat. That boils water. So we get some high pressure, high temperature steam. We run that through a turbine. So now we have low pressure, maybe steam, maybe it's a little bit of hopefully it's still steam, but we could have had some condensation here, right? But then we want to condense this all the way back down to water because it's relatively easy, or it doesn't take much power to increase the pressure of a liquid because it's incompressible, but it takes more power to compress something like steam. So here we like to cool this all the way down, right? This is why you see the big cooling towers outside of power plants, because they're trying to cool this steam back to liquid water so we can increase the pressure again and just go around and around in this cycle, right? Now, the way that we're going to approach sort of this kind of cycle analysis is by looking individually at each one of these components. So the pump is an open system where water is coming in and out, but we're changing the state of the fluid. The boiler, right, we're adding heat and that changes the state of the fluid. The turbine tries to take some of that energy out of the fluid, right, and use it to turn it into usable mechanical energy, right? And then condensing, we get this steam, we take some energy out and try to get liquid water. So what we're trying to do is integrate a bunch of pieces, individual components into a big system, right? So, and if we can learn how to do that, and as we do this through the course, we're going to learn about nuclear power plants, right? Or maybe coal power plants. I'm not sure which this is a picture of. We're going to learn about automobiles. We're going to learn how jet engines work. And we're going to learn how air conditioners work, right? And the way that we're going to do this is we're going to break down what's a really complicated system into a series of individual pieces. This is the best way to solve a big problem, right? Is always to break it down into smaller, more manageable pieces, right? So we can think about this power plant as a Lego block. So we're putting together things like pumps and boilers and turbines and condensers, and we put them together in creative ways, and then we get really cool things like power plants, right? So we're at the point now where we're going to start to look at how do we deal with an open system process, which is like an individual Lego block here. Because if I can understand how to deal with any individual Lego block, then maybe I can start to use my creativity to solve problems by putting these Lego blocks together in really interesting ways so that we can start to solve problems that we face as a society. So here we're trying to learn about these open systems. So the question whenever we, kind of go and look big picture with this kind of stuff is, well, why do we care, right? We care because we're engineers, right? And this is, a lot of people talk about engineering like it's only kind of the sum of being able to do physics and do math. But that's not really true. I mean, those are important skills, but I think that the great engineers know about creativity, right? And know how to creatively put ideas together to solve problems. And what we're doing today and throughout the course will be, we're going to learn how to solve these individual types of components, how we can analyze them. And then we're going to figure out how do we put those components together to make something really cool, right? To make something useful. So what are the kinds of blocks that we're going to be using, right? Because obviously we're not dealing with Lego when we're making a power plant, right? So the most important types of components that we're going to deal with are turbines, right? So with a turbine, you have high energy fluid coming out, and it's used to drive these fan blades and turn this shaft to create mechanical power. You have a pump, which is kind of the opposite. We plug this into the wall so that these fan blades are spinning and we're adding energy to the fluid. We have a throttle valve, which is not necessarily all that exciting. Here the pressure drops but there's not really much change in energy. We have heat exchangers, so this is pretty useful. So sometimes you have a hot fluid and you want to cool it down, right? So, if you think about the radiator in the front of your car, so that radiator fluid is hot, but we want to cool it down so we can go back into the system and cool more things down, right? So the air is moving over the fins inside your radiator, and that's cooling that fluid down, right? So that's an example of a heat exchanger. And then we have things like nozzles and diffusers. And I think the best way that we can think about this is, if you've ever had a garden hose and you use your thumb to sort of decrease the cross-sectional area that the flow goes through, what happens is you increase the kinetic energy, right? You increase the velocity of that flow because it now has to squeeze through a smaller opening, right? So that's in the nozzle, right? You're making the cross-sectional area smaller. Diffuser is the opposite of that, where you make the cross-sectional area bigger, which slows the flow down. So how do we do it, right? So here we're going to take a complicated system and we're going to break it down into its constituent parts. Then we'll do conservation of mass on all these different parts. Then we'll do conservation of energy, this equation that we just learned, right? And we'll end up treating most of these components like a simple system. You may remember when we were talking about closed systems that a simple system was one where either the heat transfer or the work was equal to zero. So we're going to look at each one of these systems, right? So a turbine and a pump, turbine gets power out, a pump consumes power, a boiler puts heat in, and a condenser has heat leave. So usually we'll treat these components as if only one type of energy is happening, energy change. So we'll get rid of either the heat transfer or the work term. Then we'll find the power or the heat transfer rate. So here's some examples, right? We'll start with nozzles and diffusers. So the point of this is change the cross-sectional area so that you can change the velocity of the fluid that's moving through, right? So it's about kinetic energy. So the assumptions that you're often going to make for a nozzle and a diffuser, right? So we write out our whole first law. And again, I'm going to tell you, always start writing out the whole first law, right? So if we're at steady state, then we get rid of this energy stored term, the storage term, right? So here, this is going to be one inlet and one outlet for most diffusers that we talk about. So we don't have to worry about the summation of these terms at all the inlets and all the outlets because there's only one of each, right? If it's adiabatic, right, that means that it's well insulated. So the purpose of a nozzle and a diffuser is not to transfer heat. So we're going to assume that the heat transfer is zero here. We're also going to assume that it's passive. So passive means that there's no power generated by fan blades inside the system, right? So the trick here, I think, is to look, does my component have fan blades in it, right? So is it like a pump or a turbine or a compressor where we have fan blades? Or is it like a diffuser that doesn't have any fan blades in it? We're going to assume that the elevation change is not that important here, right? The fluid's moving across the same center line, so we're going to say that that's the change in the potential energy due to gravitation is equal to zero, right? And now we're going to get this term, right? We have zero on the left-hand side. I'm going to divide by the mass flow rate so that it drops out. And now I'm going to get the enthalpy in minus the enthalpy out is equal to the velocity in squared minus the velocity out squared all over 2. Now, if I'm doing this, right, my spidey sense starts tingling because I got this kinetic energy term. I know that the units here are going to be messed up, right? And this is written as if it's in metric. If this is in imperial, then I would have to add that GC in the denominator as well. So what about turbines, right? So like we've said, turbines are kind of extracting power from the fluid, right? You have this high energy fluid that comes in and it turns these fan blades and turns this shaft. So here there's fan blades inside, so the power term is going to be important. So again, we start with our first law. Steady state, so that first term goes away. One inlet, one outlet, so the summation sign goes away. There's no heat transfer, right? Because we're interested in power. We're going to make all these things simple systems. I'm going to say that the change in kinetic energy is really small compared to the change in the enthalpy, and that the change in the gravitational potential energy can be neglected. And if I do this, I'm going to get that the power that's extracted by the fan blades is equal to the mass flow rate times H in minus H out. Because this is a turbine produces power, right? So work out is positive. So I would expect this term to be positive. So H in should be bigger than H out. So I have higher energy fluid coming in and a lower energy fluid going out. So next we'll talk about compressors and pumps. The big difference here is that a compressor increases the pressure of a gas, and a pump increases the pressure of a liquid. Thermodynamically, they're basically the same. And the analysis here is going to look just like it did for a turbine, where we'll say that it's at steady state, that there's one inlet and one outlet, that there's heat transfer is very small compared to the power, that the kinetic energy change can be neglected, and the potential energy change can be neglected, and we get that the power is equal to m dot times H in minus H out. This is the same equation that we got when we were talking about the turbine. The difference here is that the pump consumes power. So the pump we plug into the wall, and that makes the fan blades spin. And because the fan blades are spinning, we put more energy into the fluid. So here we would expect the enthalpy at the outlet to be bigger than the enthalpy at the inlet. And this is what I was talking about, where the textbook kind of loses the sign convention here. So I'm going to tell you we should use this hip to win sign convention throughout the whole course. So I'm going to say that this power produced by the pump is negative. Now, if you're a pump producer, right, if you're selling pumps, maybe that doesn't sound so great. You don't want to say like, oh yeah, my pump produces negative 10, kilowatts, right? You don't want to do that. But thermodynamically, this makes sense to me that this is negative. Plus, the textbook, because they sort of start to treat everything as absolute values, they're going to tell you sometimes power is m dot times HO minus H in, and sometimes power is m dot times H in minus HO, and then sometimes the power is positive, and sometimes the power is negative, and you got to memorize all that stuff. But me, I don't like memorizing things. I like understanding things from first principles, right? And if I know what my first law equation looks like, and I know the assumptions that I'm using to analyze my system, then what's going to happen is that my pump and my turbines are always going to be m dot times H in minus H out. And the first law is going to tell me whether or not it should be positive or negative. So turbines and pumps, they look the same, right? We get mw dot is equal to m dot times H in minus H out. Again, I want to encourage you to get this from the first law. But there's a little mnemonic device, a little bit of a trick that I use, right? And maybe it's because we watch too many Disney films at home, right? But this power, right, it's about work. And I know from years of watching Disney films with my children that the hardest working people in all of Disney are the dwarves, right? So if I'm trying to find work, I think about the dwarves. And the song that the dwarves sing is Hi Ho. So if I'm trying to calculate power, it's m dot times hi ho, or H in minus H out. It's a bit of a silly way to remember. And again, I think the best way to remember is just start with the first law. But this is the way that I remember which one is which, right? And then I let the first law deal with the sign of my answer. So this comes from hip to win, tells me whether or not it's positive, like a turbine, or negative, like a pump or a compressor. Right? And remember, hip to win is work in is negative, which also means that work out is positive. So a turbine produces power, so that's work out of the system, and a pump consumes power, that's work into the system. Okay, so heat exchangers can be a little bit trickier, right? So there's two different kinds of heat exchangers we can think about. So one is a shell and tube heat exchanger. This is, we talked about, so here you have two fluids that don't mix, right? So you have one fluid that's running through the tube here, and it doesn't mix with the fluid that runs over the shell. So maybe you have water on the outside and hot oil on the inside, and this is used to cool the oil down, right? You don't want to mix the water and the oil together inside of a basin to mix the heat, right? So this is a shell and tube type heat exchanger, but you can also have a direct mix type heat exchanger. So this is probably better if you have maybe steam coming in here and liquid water coming in here, and they mix together, and because they have different temperatures, then they, equilibrate to some kind of average temperature coming out here, right? So that's kind of a direct contact heat exchanger. That's this first type. And then the shell and tube type where it's like Ghostbusters, right? So here the streams don't mix, right? And here the streams do mix. So how do we deal with a heat exchanger, right? So if we're dealing with a heat exchanger, again, we're almost always in this class going to say it's steady state, that it's passive, that it's adiabatic, right? And this is kind of a tricky part, right? So this is, if I'm doing my first law analysis, heat exchangers, we'll get to an example with heat exchangers, and they can be a little tricky because there's maybe 2 or 3 choices that you can make. And sometimes you have to make all of those choices to get different equations, right? But if I'm thinking about the whole heat exchanger, so here, say my hot fluid is in the tube and my cold fluid is in the shell. So I'm definitely going to get heat transfer between the hot fluid and the cold fluid. But if the whole system is adiabatic, right? So if I wrap this whole heat exchanger in lots of insulation, so it's really, really well insulated, what this means, if it's adiabatic, that all the fluid from the hot side goes into the cold side, right? So here, if we're at steady state, we're passive, we're adiabatic. We're going to say the kinetic and potential energy changes can be neglected. Then what we're going to get, if we look at the whole heat exchanger, is that 0 is equal to the sum of the mass flow rate in times the enthalpy in minus the sum of the mass flow rate out times the enthalpy out. And we'll do some examples of all these things as we move on. So another thing that we might do is a throttling valve. So here you'll see, so this is, you have these in air conditioners and refrigerators. Basically, it's a way to lower the pressure inside the system, right? So it reduces pressure. Throttling devices are not very exciting thermodynamically. They're at steady state. They're one inlet, one outlet. They're passive, so there's no power. They're adiabatic, so there's no heat transfer. There's no change in kinetic energy. There's no change in potential energy, right? So now, because we really get m dot h in minus m dot h out is equal to 0. But if there's only one inlet and one outlet, what conservation of energy is going to tell us is that the mass flow rates are the same. So we divide both sides by the mass flow rate, and we find that the enthalpy in is equal to the enthalpy out. So we change pressure, but we don't change the enthalpy in the fluid. So I know it's kind of a lot to take in, and don't worry, we will do lots of examples, and I think we'll probably get a better handle of these things as we start to do examples. But hopefully this gives you some idea, first, of what that first law looks like for open systems, and second, how we can then start to use the first law. And I'm going to say always start with the first law, right? And so how do we use the first law, make some assumptions to get equations that are relevant for the individual components that we're working on. So that's it for today. Thanks for sticking with me, and I'll see you again next time on Thermodynamics.